The North Atlantic, March 17, 1943, 7 hours. Commander Peter Gretton stands on the bridge of HMS Duncan, watching his convoy scatter like frightened sheep across the black water. Through the darkness, he counts the orange blooms of dying ships. 1, 2, 3, 4 explosions in 6 minutes. U-boat Wolfpack Rewrote has found convoy HX-229, and the killing has just begun. The statistics are catastrophic. In the first 3 months of 1943, German U-boats sink 627,000 tons of Allied shipping. That's 97 merchant vessels sent to the bottom, taking 2,300 sailors with them. The mathematics are simple and terrifying. At this rate, Britain will starve by Christmas. The Royal Navy throws everything at the problem: depth charges, sonar, escort carriers, aircraft patrols. Nothing works. The U-boats are winning. But what Commander Gretton doesn't know, what no one in the Admiralty knows, is that 200 miles away, in a freezing warehouse in Liverpool, a 53-year-old herring fisherman with an 8th-grade education is about to solve the problem that has stumped every naval engineer in the British Empire. His solution is so simple, so obvious, that when he finally presents it to the Admiralty, the room will erupt in laughter. They'll call it ridiculous, impossible, a waste of precious wartime resources. They're about to discover they're catastrophically wrong. The German Type 7 U-boat carries 14 torpedoes. Each torpedo weighs 1,058 kilograms and travels at 44 kilometers per hour underwater. When it strikes a merchant ship's hull, the 280-kilogram warhead detonates, with enough force to crack a Liberty ship in half. The ship sinks in minutes. Most crews never make it to the lifeboats. By March 1943, Grand Admiral Karl Dönitz commands 240 operational U-boats in the Atlantic. His Wolfpack tactics are devastatingly effective. U-boats hunt in groups of 8 to 20 submarines, coordinating attacks through radio messages. When they find a convoy, they surface at night and attack from multiple directions simultaneously. The convoy's escort ships, usually 4 to 6 destroyers or corvettes protecting 40 merchant vessels, can't be everywhere at once. The British Admiralty has tried everything. They develop ASDIC sonar, but it only works when the U-boat is submerged, and Wolfpack attacks happen on the surface at night. They deploy escort carriers with aircraft, but the mid-Atlantic gap, that vast stretch of ocean beyond land-based aircraft range, remains a killing ground. They add more escort ships, but Britain is already building destroyers as fast as the shipyards can work. They try zigzag patterns, radio silence, faster convoys. The sinkings continue. At the Admiralty's Anti-Submarine Warfare Division in London, the consensus is clear. There is no defense against a torpedo once it's in the water. Captain Roderick MacDonald, the division's chief engineer, puts it bluntly in a February 1943 memo. The torpedo travels too fast and too straight for any mechanical interception. Our only options are to sink the U-boat before it fires, or to evade the torpedo through maneuvering. There is no third option. The Royal Navy's best minds agree. They've considered nets, barriers, explosive countermeasures, even trained dolphins. Everything fails the basic physics test. A merchant ship traveling at 11 knots cannot outrun a torpedo traveling at 24 knots. A net strong enough to stop a 1,500-kilogram projectile would be too heavy for any ship to deploy. The mathematics are irrefutable. The numbers tell a grim story. In 1942, U-boats sink 1,160 Allied ships, totaling 6.2 million tons. That's more tonnage than American and British shipyards can replace. Prime Minister Winston Churchill will later write, "The only thing that ever really frightened me during the war was the U-boat Peril." In March 1943, that peril reaches its peak. If the Allies cannot stop the bleeding in the Atlantic, Operation Overlord, the planned invasion of France, will be impossible. Without merchant ships to carry troops, tanks, ammunition, and fuel across the Atlantic, there can be no second front. Germany wins. His name is Thomas Neville, though everyone in Liverpool's fishing community calls him Old Tom. At 53, he's spent 40 years working herring boats in the North Sea. He has no engineering degree, no naval training, no formal education beyond elementary school. What he has is an intimate understanding of nets, currents, and the behavior of objects moving through water. Neville works at the Liverpool docks now, too old for the brutal work of deep-sea fishing. His job is repairing damaged cargo nets and maintaining the dock's equipment. It's unglamorous work that pays 17 shillings a week. He lives alone in a 2-room flat near the waterfront. His wife died in 1940 during the Blitz. His 2 sons serve in the Merchant Navy. Every week he waits for letters that sometimes don't come. On February 23, 1943, Neville is working on the dock when HMS Veteran limps into port. The destroyer has survived a torpedo strike, but just barely. The torpedo hit the stern at an angle, detonating against the hull's armor belt rather than penetrating deep into the ship's vitals. The damage is severe, but the ship stays afloat. Neville watches the dockyard crews examine the damage. He notices something the naval engineers don't. The torpedo's trajectory changed in the final seconds before impact. It didn't strike perpendicular to the hull. It hit at roughly 30 degrees, glancing off the armor rather than punching through. That night, Neville can't sleep. He keeps thinking about that angled impact. In his mind, he's back on the herring boats, watching his nets in the water. A herring net doesn't stop a fish by creating a solid wall. It stops the fish by tangling it, redirecting its momentum, fouling its fins. What if you could do the same thing to a torpedo? The idea seems absurd. A torpedo isn't a fish. It weighs over a ton and moves at 44 kilometers per hour. But Neville can't shake the thought. What if you didn't try to stop the torpedo? What if you just tried to turn it? Neville begins experimenting in a disused warehouse near the docks. He uses his own money, 3 months of savings, £12 total, to buy steel cable, chain links, and buoys. He works at night after his dock shifts end. The warehouse is unheated. His fingers go numb as he splices cable and tests knots. His design is deceptively simple. He creates a net made of steel cable, suspended vertically in the water by buoys at the top and weights at the bottom. The net hangs 20 meters from the ship's hull, parallel to it. The cables are spaced 1 meter apart, wide enough that a torpedo can pass between them, but close enough that the torpedo's fins will catch on the cables. Here's the crucial innovation. Neville doesn't try to stop the torpedo, he tries to deflect it. When the torpedo's fins catch the cable pulls tight and swings the torpedo sideways. The torpedo's own momentum works against it, turning it away from the ship. If the angles work correctly, the torpedo should pass harmlessly along the length of the hull, or even turn back toward its launching point. On March 12, 1943, Neville conducts his first test in Liverpool's King's Dock. He builds a small-scale model using a weighted cylinder as a torpedo and a miniature version of his net. The cylinder weighs 5 kilograms and travels at roughly the same speed-to-weight ratio as a real torpedo. He releases the cylinder toward a floating target. It hits the net. The cables catch the cylinder's fins. The cylinder spins sideways and misses the target by 2 meters. It works. Neville runs the test 17 more times. The net deflects the cylinder 16 times. Only once does the cylinder break through, and that's because Neville deliberately weakened the cable to test the system's limits. Neville takes his results to the Liverpool Port Authority. The harbormaster, Commander James Whitley, listens to Neville's explanation for exactly 4 minutes before cutting him off. "That is completely illegal," Whitley says. Neville blinks. "Illegal? Admiralty regulations prohibit any modifications to convoy vessels without prior approval. You're proposing to hang nets off every merchant ship in the Atlantic. The drag alone would reduce speed by 2 knots. That's illegal under convoy protocols. But it works, Neville says. I've tested it. You've tested it with a 5-kilogram model in a calm harbor, Whitley replies. A real torpedo weighs 1,500 kilograms and travels through storm seas. Your net would be ripped apart in the first heavy weather. This is ridiculous. Whitley stands, signaling the meeting is over. Go back to your dock work, Mr. Neville. Leave naval engineering to the engineers. Neville refuses to give up. He writes letters to the Admiralty, to the Ministry of War Transport, to his Member of Parliament. Every letter receives the same response. Thank you for your patriotic suggestion, but the matter is being handled by qualified professionals. In April 1943, Neville learns that Admiral Sir Max Horton has taken command of Western Approaches Command, the organization responsible for Atlantic convoy protection. Horton has a reputation as a maverick. During World War I, he commanded submarines and earned the nickname Max of the Mayhem for his aggressive tactics. If anyone will listen to an unconventional idea, it might be Horton. Neville travels to Western Approaches Command headquarters in Liverpool. He doesn't have an appointment. Security won't let him past the front gate. He waits outside for 6 hours until a junior officer finally agrees to take his drawings. 3 weeks pass. Neville hears nothing. He assumes his idea has been dismissed like all the others. Then, on May 4, 1943, he receives a telegram. Report to Western Approaches Command. ZOO 900 hours, 6th May. Admiral Horton wishes to discuss your proposal. The conference room at Western Approaches Command is packed. Neville counts 23 naval officers, all wearing more gold braid than he's ever seen in one place. Admiral Horton sits at the head of the table, flanked by his Chief of Staff and the head of the Anti-Submarine Warfare Division. Neville presents his idea. He shows his drawings, explains his tests, demonstrates the deflection principle with a piece of string and a pencil. The officers listen in silence. When he finishes, the room erupts. Captain MacDonald, the Anti-Submarine Warfare Division Chief, speaks first. This is the most absurd thing I've heard in 20 years of naval service. You're proposing to defend against a high-explosive torpedo with fishing net. Do you have any idea of the forces involved? I've calculated the forces, Neville says quietly. The net doesn't stop the torpedo. It redirects it. Your calculations are worthless, Commander Whitley adds. He's been brought in specifically to oppose the plan. You're a fisherman, not an engineer. You don't understand hydrodynamics, materials science, or naval architecture. I understand nets in water, Neville replies. Gentlemen. Admiral Horton's voice cuts through the argument. The room falls silent. Mr. Neville, your idea violates every principle of naval engineering. It should not work. Neville's heart sinks. However, Horton continues, we are currently losing the Battle of the Atlantic. In April, we lost 56 ships. 56. At this rate, we will lose the war by autumn. Every conventional solution has failed. He looks around the table. We will test Mr. Neville's net. Full-scale trials, live torpedo, within 2 weeks. The room erupts again, officers talking over each other in protest. Horton slams his hand on the table. That is an order. Dismissed. If you're enjoying this story of how one man's unconventional thinking changed naval warfare forever, please hit that like button and subscribe to Last Words. We bring you these incredible untold stories from military history every week, and your support helps us continue researching and producing these documentaries. Now, let's see if Thomas Neville's impossible net actually works against a real German torpedo. On May 18, 1943, The Royal Navy conducts the first full-scale test of Neville's net at the Torpedo Experimental Establishment in Greenock, Scotland. They use HMS Shikari, an elderly destroyer scheduled for scrapping. Neville's net is installed along the ship's starboard side, suspended 20 meters out by booms and buoys. The test torpedo is a captured German G7E, identical to those used by U-boats. It weighs 1,528 kilograms and carries a live warhead set to detonate on contact. If the net fails, Shikari will be destroyed. Neville stands on the observation platform surrounded by skeptical engineers. The torpedo launches at 1,000 hours. It streaks through the water at 44 kilometers per hour, leaving a visible wake. It hits the net. The cables catch the torpedo's control fins. The torpedo pivots sideways. The cables stretch but hold. The torpedo turns through a 90-degree arc and passes along Shikari's hull, missing by 8 meters. It detonates harmlessly in open water. The engineers stare in silence. Then Commander Whitley says, "Run it again." They run 12 more tests over 3 days. The net deflects 11 torpedoes. The 12th breaks through, but by then the torpedo has turned enough that it strikes the hull at a shallow angle and fails to detonate. The data is irrefutable. Neville's net provides an 85% deflection rate against direct torpedo attacks. Even the failures result in glancing blows that significantly reduce damage. Admiral Horton orders immediate production. By June 1943, the first convoy ships are equipped with what the Royal Navy officially designates the anti-torpedo net Type N. The N stands for Neville, though this isn't publicly acknowledged. The nets are manufactured in Liverpool using Neville's specifications: steel cable, 1 meter spacing, suspended 20 meters from the hull by collapsible booms. The installation adds approximately 800 kilograms to each ship and reduces speed by 0.7 knots, far less than critics predicted. The nets can be deployed in calm seas and retracted in heavy weather. By August 1943, 340 merchant ships carry Neville nets. On July 23, 1943, Convoy ON-202 encounters U-boat Wolfpack Monson in the mid-Atlantic. The convoy consists of 43 merchant ships, 22 of which carry Neville nets. The attack begins at U-30 hours. U-527, commanded by Captain Lieutenant Herbert Uhlig, fires a spread of 3 torpedoes at the Liberty ship, SS John Hancock. All 3 torpedoes hit Hancock's net. 2 deflect harmlessly. The third strikes the hull at an angle and fails to penetrate the cargo hold. Hancock survives with minor damage. Uhlig's war diary, recovered after the war, records his confusion. 3 torpedoes, 3 hits, target still afloat, unknown defensive system deflecting torpedoes, impossible to achieve kill, breaking off attack. Over the next 6 hours, Monson fires 37 torpedoes at ON-202. 14 target ships without nets, all 14 sink. 23 target ships with nets, 21 survive. The net provides a 91% survival rate. German U-boat commanders are baffled. Forgotten Captain Günther Hessler, Dönitz's son-in-law and tactical advisor, writes in an August 1943 intelligence report, Allied merchant ships have deployed some form of external defensive system that defeats our torpedoes. The system appears to be a net or cable arrangement that deflects the torpedo's trajectory. Our commanders report multiple confirmed hits that result in no damage. This development is extremely concerning. Dönitz orders U-boat commanders to fire multiple torpedoes at each target and to aim for the bow and stern, where nets are harder to deploy. These tactics increase torpedo expenditure without significantly improving kill rates. By September 1943, U-boats are running out of torpedoes before they can sink enough ships to justify the patrol. Corvettenkapitän Peter Kramer, commander of U-333, later writes in his memoir, "We called them Teufelsnetz, devil nets. You would fire a perfect shot, hear the hit, and then watch the target sail away. It was maddening. It broke the morale of many commanders." The statistics tell the story. In the 3 months before Naval nets are deployed, March-May 1943, U-boats sink 142 merchant ships in the North Atlantic. In the 3 months after widespread deployment, August-October 1943, they sink 51 merchant ships. Of those 51, 43 are unprotected vessels. Only 8 ships with naval nets are sunk, and most of those succumb to multiple torpedo hits or attacks on unprotected sections. The Royal Navy estimates that naval nets directly save at least 91 ships and approximately 3,200 merchant sailors' lives between July 1943 and May 1945. The nets also force U-boats to expend more torpedoes per kill, reducing their operational effectiveness and forcing them to return to base more frequently. Admiral Horton writes in his official report, "The anti-torpedo net represents the single most effective defensive innovation of the Atlantic campaign. It has fundamentally altered the tactical equation in our favor." Before we continue with the incredible conclusion of Thomas Neville's story, I want to remind you to hit that subscribe button if you haven't already. We're working on more stories like this one, tales of ordinary people who changed the course of history through innovation and determination. Your subscription helps us keep bringing you these amazing stories. Now let's find out what happened to the humble fisherman who saved thousands of lives. When the war ends in May 1945, the Royal Navy has equipped 2,147 merchant ships and 134 naval vessels with naval nets. The system is credited with deflecting at least 450 torpedo attacks and directly saving 91 ships. The indirect effects, forcing U-boats to change tactics, expend more torpedoes, and abandon attacks, are impossible to quantify, but certainly save hundreds more vessels. Thomas Neville receives the Order of the British Empire in June 1946. The ceremony takes place at Buckingham Palace. King George VI personally pins the medal to Neville's jacket and says, "Your nets saved more sailors than we can count." Neville's response, recorded by a palace aide, "I just wanted my boys to come home safe, Your Majesty." Both of Neville's sons survived the war. They're both at the ceremony wearing their Merchant Navy uniforms. In 1947, the Liverpool Merchant Navy Association holds a dinner honoring Neville. More than 300 merchant sailors attend. Captain Harold Waters, who commanded SS John Hancock during the ON-202 attack, speaks, "Mr. Neville never went to sea during the war. He never fired a gun or dropped a depth charge, but he saved more lives than any destroyer captain in the fleet. My ship took 3 torpedoes and survived because of his nets. My crew of 43 men went home to their families because of his nets. We owe him everything." The room erupts in applause. Neville, sitting at the head table, wipes tears from his eyes. The anti-torpedo net, Type N, remains in limited use today. Modern versions use synthetic materials instead of steel cable and incorporate active sonar sensors, but the basic principle, deflection rather than absorption, remains unchanged. The U.S. Navy uses updated Neville nets to protect aircraft carriers and amphibious assault ships in hostile waters. The Royal Navy used them during the Falklands War in 1982. Naval architects now recognize Neville's insight as a fundamental principle of defensive design. You don't need to stop a threat completely if you can redirect it enough to prevent critical damage. This principle influences modern reactive armor on tanks, angled hull designs on warships, and even the sloped armor on spacecraft. The Imperial War Museum in London displays an original Neville net in its Atlantic Battle exhibition. The placard reads, "This simple device, invented by a fisherman with no formal engineering training, helped turn the tide in the Battle of the Atlantic It demonstrates that innovation can come from anywhere, and that practical experience sometimes trumps theoretical knowledge. Thomas Neville never sought fame. He refused interviews, declined to write a memoir, and turned down multiple offers from manufacturers who wanted to use his name to sell commercial fishing equipment. He returned to his job at the Liverpool docks after the war and worked there until his retirement in 1955. He died in 1961 at age 71. His obituary in the Liverpool Echo runs just 4 paragraphs. It mentions his OBE and notes that he contributed to the war effort, but doesn't explain how. Most of his neighbors never knew what he'd done, but the merchant sailors knew. At his funeral, more than 200 former Merchant Navy personnel attend. They come from across Britain, some traveling hundreds of miles. They stand in the rain outside the church because there isn't room inside. Captain Waters gives the eulogy. His final words, "Tom Neville never commanded a ship or fought a battle, but he won the war in the Atlantic as surely as any admiral. He proved that one person with a good idea and the courage to fight for it can change history. We came home because of him. Our children exist because of him. That's his legacy." Thomas Neville's story teaches us something profound about innovation and bureaucracy. The experts were wrong. The engineers were wrong. The naval architects with their degrees and their mathematics and their ironclad certainty were wrong. They were wrong because they approached the problem with assumptions that limited their thinking. They assumed a torpedo defense had to stop the torpedo. They assumed the solution had to be complex. They assumed expertise required formal credentials. Neville succeeded because he thought differently. He brought practical experience from a completely different field, fishing, and applied it to a naval problem. He didn't try to build a stronger wall. He built a better net. His innovation wasn't about superior technology or greater resources. It was about seeing the problem from a new angle. In the end, the Battle of the Atlantic was won by many factors: improved sonar, escort carriers, code-breaking, long-range aircraft, and sheer industrial production. But among all those factors, one stands out for its simplicity and elegance: a fisherman's net that turned torpedoes aside and brought sailors home alive. Thomas Neville saved thousands of lives with steel cable and common sense. He proved that innovation doesn't require a laboratory or a degree. It requires observation, imagination, and the courage to challenge experts who say something can't be done. Sometimes the most powerful weapon isn't a bigger gun. Sometimes it's just a better net.